For this next section, we're going to explore limits at infinity and asymptotes a little bit more, focused on horizontal asymptotes here, but I want to spend a little bit of time recalling infinite limits and our vertical asymptotes as well. So, looking at a function and considering different types of infinite behavior, looking at when the function approaches infinity, grows without bound or decreases without bound, but also when we let our x grow without bound or decrease without bound. So the tail ends of the graph, if you want to think of it that way, the far left and the far right side of the graph. What occurs as our x's decrease without bound, go to the far left of the graph, or increase without bound, go to the far right of the graph. So first, let's just start with a quick little recall on infinite limits. So we say that the limit of a function as x approaches a grows or decreases without bound, and we capture that behavior using this infinite notation. We say that the limit of f of x as x approaches a is, we do say equals positive or negative infinity, although we can't ever really be equal to infinity, right? Infinity is a concept and not a number. So we're using that symbol, that mathematical symbol, just to capture that behavior that we are either growing without bound or decreasing without bound. We also have the left and the right-sided limit where we can talk about it that way too. So let's just do a quick, this is coming out of a previous section, but I want to do a quick recall on how we compute this. This is a nice section, and I've layered it into this section to recall these and practice these type of limits as well. So what if we wanted to do this limit? We wanted to find the limit of the function 3x over x squared minus 4 as x approaches -2. Now, if I try just my direct substitution, this is our process so far, we would get -6 over 0. And what that has indicated to us is that we have some kind of infinite behavior, because we have a constant in the top and then we have something that is approaching 0 in the bottom, getting infinitely small, if you want to think of it that way. So what we have to decide though is, right, does this go to positive or negative infinity? We got to figure that out. That's a question mark. We don't know. So we got to do a little bit more work. And what I would think about maybe is sometimes it helps to actually think about what we're plugging in here. So we are approaching -2 here. So we're plugging in values here. We do want to think about the fact that we're going to be plugging in values that are approaching 2, and we need to think about if we're going to 2 from the left, what happens, and what happens if we're approaching -2 from the left and from the right. So if we're coming to -2 from the left, that means that we're plugging in values like x equals -2.001. And if we're coming to 2 from the right, we're plugging in values like x equals -1.999. Okay? So we're sort of thinking about this in our heads here. But regardless, as I plug in values here, notice that we're going to square them. So I'm going to go ahead, I've written all my thought bubbles around. I'm going to go ahead and rewrite this down here so I have some space. 3x over x squared minus 4. As we're plugging in our values there, when I square these numbers that are approaching 2, this quantity in the bottom is going to be approaching, let's do it from both sides. So let's, I didn't give myself enough room there. Let's do the left and let's do the right. So as we approach from the left, we're going to take our 3x over x squared minus 4. And as we come from the left, when I take that number negative, a number coming from the left, so it's slightly more negative than -2, and I square it, this denominator is actually, in the top, we're still going to have our -6, but in the denominator, this number in the bottom is going to be approaching 0 from the right. It's going to be positive because as I square this, notice that little square right there, this quantity x squared, if we're slightly to the left of -2, is going to become bigger than 4 when I square it. So then when I subtract 4, I've got that 0 from the right, and this would be negative infinity. And then on the right side, as we take our limit as x approaches -2 from the right, and I take my 3x and my x squared minus 4. Again, thinking about what I'm plugging in, the numerator is still going to be -6. And then in the denominator, we're going to be approaching 0, but how do we approach 0? Well, as we're approaching -2 from the right side, so we're plugging in a number like -1.999. So when we square that number, that's going to be slightly less than 4 because we're to the right side of -2. So we're slightly less than 4. When I subtract that 4, that is going to become a negative number, a very small negative number, but a negative number. So we're going to be approaching 0 from the left. And when you take a negative and divide by a negative, you would get a positive number, and it will be increasing without bound. So notice that our left-hand limit and our right-hand limit are both infinite, but they are not both growing without bound or both decreasing without bound. On one side, we're decreasing without bound. On the other side, we're increasing without bound. And so what we would actually have to say here is that this limit, we can't capture that infinite behavior. It's not the same. So we'd have to say the limit as x approaches -2 of 3x over x squared minus 4 does not exist. We could say the left doesn't equal the right. We have infinite behavior, but the two sides do not do the same thing. Okay. We do have some infinite behavior, but the two sides don't do the same thing. So let me get that all on the screen at the same time. And that's our little recall. So that's looking at infinite behavior as we approach a point. So now we're going to expand this idea, not this particular idea, but we're going to expand our knowledge of limits, and we're going to say, what if instead of just looking at a single point, what if we want to let x increase without bound or decrease without bound? So this is kind of, rather than looking at a specific point and considering if it might have infinite behavior at that point, what's going to happen as our x's grow or decrease without bound? So let's take a look at that. So here we're going to look at a couple of graphical examples first, and then we'll have our intuitive definition. So once again, we often want to know what's the end behavior of a graph. What's happening as x is becoming very large, approaching infinity, or as x becomes very small, x approaches -infinity. And that's the end behavior of a graph if we're looking at it graphically. So on this first little graph that I have here, let's just say we've got this function, kind of this is a bell-shaped curve. Say we're looking at a bell-shaped curve, and that has some very interesting behavior at the ends, right? The actual function here, we should define this, y is equal to f of x. This actual function right here is approaching the x-axis on both ends of the graph. And so how do we say that mathematically? Well, mathematically, we would say that the limit as x grows without bound of the function is 0. So the limit of the function as x grows without bound is equal to 0. It's approaching 0, which is the x-axis. And as well, the limit of the function as x decreases without bound is also 0. So x approaching infinity or x approaching -infinity, that's a way of saying that x grows without bound or decreases without bound. So we can see that that's happening on the tail ends of this graph. Now graphs don't always approach a single value. Sometimes they increase without bound or decrease without bound as x is increasing or decreasing without bound. This particular graph, I created a little graph here where we had kind of different behavior on both ends of the graph. So you can see as x is increasing without bound here. So as x goes, let's call this guy, I should have written this on here too, y equals f of x again. So let's call it new function, but we'll still call it f of x. So as x is increasing without bound, as we're going out towards the right side of the graph, notice that this function is, it has some kind of oscillating behavior, but it's going towards a single value L. So I drew in, this is actually called a horizontal asymptote. I drew in a horizontal asymptote right here. We'll define it in a couple minutes here. But it's a horizontal asymptote. This function is approaching that value, getting infinitely close to that. That's how we say that mathematically, getting infinitely close to that value y equals L as the x's increase without bound. So the x's are increasing without bound, and the function values are approaching this one single value L. So we say that this way. We say the limit of the function as x approaches infinity, which means grows without bound, is equal to L. Now, notice on the other side of the graph, over here, as x decreases without bound, and I didn't type this up, but as x decreases without bound, notice that the function is actually increasing without bound. Well, how do we capture all that behavior, right? This increasing and decreasing without bound, whether it's the function or it's x, we use infinity when we're discussing that. So if we were to say the limit of f of x as x approaches negative infinity, meaning it decreases without bound, in this case is infinite or growing without bound. So there we've got function looking at the tail end, the left side of the graph as x decreases without bound, and we're saying that that is infinite. Okay, so there's some graphical examples. Let's actually have our intuitive definition. So our intuitive definition says this, and if you want to go ahead, freeze the screen here and get this intuitive definition down. Let's see, I think I'm going to put the horizontal, let's get the horizontal asymptotes definition up on the screen here as well. So the intuitive definition, so as x gets large, meaning that it heads towards infinity, as it grows without bound. Another way of saying as x gets large, that says x grows without bound. Grows without bound. Okay? So as x grows without bound, goes towards infinity, if f of x gets closer and closer to L, then we say that the limit of f of x as x approaches infinity is equal to L. So that's our intuitive definition. And the other side of the graph, as x decreases without bound, as x gets smaller, meaning it decreases without bound, it goes towards negative infinity on the x-axis. If f of x gets closer and closer to L, arbitrarily close to L, we say that the limit of f of x as x approaches negative infinity is equal to L. And we have that notation. We capture that. And a horizontal asymptote is defined to be a line L, y equals L, is a horizontal asymptote if one of those two scenarios happens. That is, x increases or decreases without bound, the function approaches L. Okay, so take a minute, write those intuitive definitions down. We are going to work with the intuitive definitions. At the end of this section, I will give you the precise definitions for these infinite limits, these limits at infinity, but we are not actually going to be doing proofs with these. We'll just talk about what those precise definitions mean. So let's look at an example. So here's an example of a graph that has both a vertical asymptote and a horizontal asymptote. And so let's take a look. Let's call this f of x. So this is y equals f of x. This line here, 1, 2, 3, this is at 4 on the graph, and obviously that is at 0 on the graph. And what we can say here is that this particular, and I have it typed up here, but when we're looking at this, we can see that there is both a vertical asymptote, that comes from our previous knowledge. We can see that there is a vertical asymptote on this graph at x equals 0, and that's because there is infinite behavior there. That's because we've got the limit as x is approaching 0 from both directions in this particular case. It wouldn't matter as long as there's infinite behavior, at least on one side, left or right. But it turns out on the left and the right, this function is decreasing without bound. So there's definitely a vertical asymptote, and I use VA to abbreviate vertical asymptote. And then HA, there's a horizontal asymptote. Turns out that there's just one horizontal asymptote. You can have more than one horizontal asymptote. The behavior at the far left of the graph as x approaches negative infinity is not necessarily going to be the same as the behavior on the right side of the graph. So we'll look at our next example. We'll show one where we have two horizontal asymptotes. So a horizontal asymptote here is, and we do always write these as actual lines, like x equals 0, that's a vertical line. Y equals, in this case, is going to be y equals 4 is the horizontal asymptote. And the reason we have a horizontal asymptote at y equals 4 is because on both sides of the graph, so we'll write both of these at the limit of this particular function as x approaches infinity is equal to 4. So as x is approaching, growing without bound, the function is approaching that horizontal line 4. And also on the other side of the graph, the limit as x approaches negative infinity of f of x is also 4. So we have both our horizontal asymptote and our vertical asymptote. Now, vertical asymptotes were defined before when we talked about a function having growing or decreasing without bound. As we approached a value a function having an infinite limit. Here we're talking about limits at infinity, and so I want to keep kind of reminding us that we can look in both at both types of limits, both infinite limits and limits at infinity. Okay? So when the function is growing or decreasing without bound, or when x is growing or decreasing without bound. All right, so that's a horizontal asymptote of a horizontal line where the function approaches that horizontal line as x either approaches infinity or negative infinity. So let's look at one. Let's look at a function that hopefully we're somewhat familiar with, the inverse tangent of x. And so the inverse tangent of x, just to give us a visual, what the inverse tangent of x looks like, and we're going to look at the limit as x both grows and decreases without bound. And what the inverse tangent of x looks like, squeeze it onto my screen here, is something like this. Okay. It is a reflection over the line y equals x of the tangent curve, properties of inverses. And since the tangent curve has vertical asymptotes at negative pi over 2 and at pi over 2, the inverse tangent curve is going to have horizontal asymptotes at pi over 2 and negative pi over 2. So this is the curve y equals, this is the graph of the function, or the curve, inverse tangent of x. And so we have this graph. So when we talk about what is the limit of inverse tangent of x as x grows without bound, we can see here that this is going to be pi over 2, positive pi over 2 as x grows without bound. So going to the far right of the graph. Going the other side of the graph, as x approaches negative infinity or decreases without bound, we can see that that is going to be negative pi over 2. So notice here that on the right side we're approaching one value of L, and on the left side another value of L, so that means that our horizontal asymptotes for this particular function are 2. We have 2 of them, y equals negative pi over 2 and y equals positive pi over 2. Okay, this is, and so if this is feeling a little fuzzy, seems like it's been a while since you've looked at the inverse tangent of x, this is something that we're going to utilize, or a function we're going to see quite a bit. We're going to work a lot with the inverse trig functions. They've started to pop up in our last couple sections, and we will see them continue to pop up throughout calculus. So this is definitely one you're going to want to, if you haven't already, commit to memory, a graph that you should know and be able to reproduce and be able to work with the inverse tangent curve. Okay, so let's do two more examples, two more graphical examples on this particular video. So let's take this, let's see if I can get this all on the screen. Let's take this graph that's given and let's compute a couple of limits. So again, putting together the pieces that we've talked about with vertical asymptotes along with now what we're talking about with horizontal asymptotes. So if this is our curve, excuse me, this is our curve y equals f of x. So if here's our curve y equals f of x, let's consider all 4 of these limits that I have listed. We could call these, let's call this A, B, C, and D. And once we're done, we'll also do E, and we'll find all asymptotes. Okay, so the limit as x, the limit of this function as x decreases without bound as x approaches negative infinity. So if we're taking a look at that, going out to this side of the graph as x is going this direction, what is happening to the function? And we can see there that the function is approaching this value. So what is that value? Well, here's my origin right here, so this would be -1. So my function is getting arbitrarily close to -1. Now let's go out the other side. So what happens as we approach or grow without bound? As x approaches infinity, which means grows without bound, goes to the far right of the graph. So what's happening on the far right of the graph? Well, on the far right of the graph, I'm going to dash out a little line here. This is approaching this numerical value. So since that's 1, this has to be 2. So we are approaching 2. And while we're talking about those are creating our two horizontal asymptotes. So again, you don't have to have a horizontal asymptote on a graph at all. You might have one horizontal asymptote, you might have two horizontal asymptotes, or you might have none. Okay? In this case, we actually have two, and we want to write them as actual lines. So let's say y equals -1 and y equals 2. All right. So let's continue with our limits. So we've found our horizontal asymptotes, we've taken our limits at the two endpoints of the graph. Now let's consider what is occurring as we approach 0. So as the function, as the x values approach 0, what is the function doing? So as we're approaching 0, notice on this graph that both sides are approaching or decreasing without bound from, so here is 0. As we approach 0 from both the left and the right, these are both, the function is going to decrease without bound. And since it occurs, the same thing occurs on both sides of the graph, we say that that is -infinity. Okay? And then on the last part here, D, what's happening to this function as we approach 2? So here's 2. As x is approaching 2, notice that we actually have two different behaviors. As we approach 2 from the left, we're approaching -infinity, and as we approach 2 from the right, we are approaching +infinity, which actually means that we will say that this does not exist because the left, and we can see that right here, because the left, I'm sorry, I've gone off the screen, because the left does not equal the right. Okay? Now, that said, x equals 2 is actually still a vertical asymptote, because our definitions for vertical asymptotes are that we have behavior that is infinite. And so both at 0 and at 2, at x equals 0 and at x equals 2, those two vertical lines, there is infinite behavior. And so when we're talking about our vertical asymptotes, we are going to say that we have two vertical asymptotes at 0 and at 2. Okay? Even though the behavior from the left and the right of 2 was different, right? One side grew without bound, the other side decreased without bound, that still makes a vertical asymptote. So let's get that whole graph and all those limits on the screen here at the same time. All right. Okay, so that's going to conclude the introduction. I'm going to save the next example to start off the next video, but that's going to conclude the introduction on our both our horizontal asymptotes and our limits at infinity, meaning as x grows without bound or decreases without bound. Also wrapped in some review here with our infinite limits, right? We got our limits at infinity and our infinite limits and vertical asymptotes.